Hello there. Welcome to the Strength of Materials video lectures. In this video lectures, we are going to be talking about volumetric strain. That indicated letter is the epsilon V. In the last video lectures, we have seen what is the longitudinal strain, what is the lateral strain, and the Poisson's ratio. Those strains are going to be indicating in the respective directions, like X, Y, and Z directions. But in this case, what will happen? We will try to assess the total volumetric changes in this member. So then how we are going to be do? The strain is nothing but the change in dimensions to the original dimensions. When I am applying for the volumetric strain, then what happened here? The same definitions I am going to be taking here, the change in volume to the original volume, right? So that's indicated later here is going to be del V by V we are going to be considering. So then further we are going to be applying the same principle for the volumetric strain. So that means when a rectangle member is going to be subjected to the uniaxial load, or maybe the multi-axial, the perpendicular stresses are going to be acting, then how that member is going to be change its dimensions, that's behavior we are going to be considering in the volumetric strain. Yeah, we learn what is the volumetric strain. Now we are trying to apply for a rectangle bar. There we can see the bar member is going to be consist of in the three dimensions. That's going to be L, B, and D. And we made it to subject it to the axial load in the direction of the length. So there we can see the some terminologies we are going to be written here. That's L is going to be length of the bar, and B is going to be width of the bar, and D is going to be depth or the height of the bar. These are the original dimensions of the component. Once the load is going to be acted on this member, as we know, some of the dimensions will get the change. That depends on the strength of the material and externally applied force. So there we can see del L is going to be change in length. If any changes, either positive or negative, we are going to be say. And the change in width we are going to be considering, that is the del B, and D is going to be change in height of that member. As you know, these are all going to be change in the dimensions after applying the load, and these are going to be the original dimensions of the component. Now we are trying to find out what is the volumetric strain. As you know, the volumetric strain already we have discussed, change in volume to the original volume we are going to be say. So suppose if I am going to be writing the original volume, what is the equations we will get it? The original volume Vi I am going to be say. Vi is going to be the original volume, that is equal to L into B into D. These are the dimensions. That's we are going to be getting mm cube. Suppose, then how could you calculate the change in volume? That's the del V is equal to, that is the change in volume, that is equal to the final volume minus initial volume I am going to be taking. The Vf minus Vi. The Vf is nothing but the final volume and minus to the initial volume. So how to calculate the Vf? As we know, when we are applying the load, there is some dimension changes will occur in the member, right? So on that basis, I am going to be writing Vf is equal to, how could you write in this case, what is the final dimensions of this component in the L directions? That I am going to be taking L plus del L into B plus del B into D plus del D. So can you see here? So original volume is equal to LBD. But the same we are going to be taking the final volume, that is equal to, because some of the changes in the dimensions also we need to be taken into the consideration. That's maybe positive or negative, that depends on the material, whether it is elongating, that means increasing the dimensions, or decreasing the dimension. That's going to be L plus del L, right? The B will become B plus del B, and D will become D plus del D. So on this basis we are trying to find out the change in volume, and then we will substitute in this equation. So now we need to find out the final volume of the component. There we can see I am going to be multiplying these terminologies over here. The first I will make this 2, and then I will make with this third part. So then that is equal to, the Vf is equal to L plus B plus L into del B we are getting, plus del L I am going to be getting B into del L plus del L del B, we got it. So then this is going to be D plus del D is there. Now I am going to be multiplying this total with this one, because we are developing the mathematical model to identify how the behavior is going to be existed for this one. That is equal to here. So then first terminologies I am going to be L, B, D I am going to be taking. The next one L, B, del D we are going to be considering. The next second terminology is plus LD del B plus L del B del D in continuation with the third one, B D del L plus B del L del D plus the fourth terminology is del L del B D we are taking plus del L del B and del D. So after the expression we are going to be multiplying and then we got it. So then what I am going to do, there is a small quantities are there. What are the small quantities? Because the change in the dimensions in the components are going to be the very small quantities. So those I am going to be here reducing. So that means I am considering these are going to be equal to 0. The multiplication of the two small quantities I am going to be making to 0. So that my equation will going to be very small. So from this equation the final volume that is equal to LBD plus LB del D plus LD del B plus BD del L, we got it. So this is going to be the final volume. Now I am going to be substituting in the change in volume. So change in volume is nothing but final volume minus initial volume we are going to be taking. So that's del V is equal to, what is the formula we had? The original volume is equal to LBD, and in this case also we do have the LBD. Right? So these two are going to be vanishing, then finally I am going to be getting here. So what is that one? So BD del L, I am going to be rearranging that equation plus next LD del B plus LB del D equation, because this terminology is going to be your original volume. Right? When I am substituting in this equation, this is also original volume, it has the negative. So then finally these two are going to be cancelled, then we got this equation. If I am going to do the further simplification in this equation, so this mathematical model del epsilon V is equal to del V by V. Now I am trying to substitute in this equation, that is equal to, this is going to be B D del L plus LD del B plus LB del D divided by LBD, we will get it. Right? And further simplification of the strain is equal to BD will going to be cancelled, del L by L plus del B by B plus del D by D. So this is going to be your volumetric strain of that member when it is subjected to the axial force. Right? So now further simplification I am going to be doing, and so that we will get in the lateral and linear strain directions. So as we know that del L by L I am going to be considering is the longitudinal strain, and del B by B and del D by D are going to be your lateral strain. So then if I am going to be simplifying these equations, how should I write it? That's going to be epsilon V is equal to, how we can write here? This is going to be your longitudinal strain plus, in this case, how many we do have? That's going to be 2 into lateral strain, I can take it, suppose. So there we can see here, I want to define this volumetric strain in terms of only the del L. So right, is it possible really? There we can see here, the longitudinal plus 2 into lateral strain directions we have taken. As we know, the Poisson's ratio is equal to the longitudinal strain divided by, this is going to be your lateral strain divided by longitudinal strain. Alright, now I am going to be simplifying this equation. The lateral strain is equal to mu into longitudinal strain. As we know, the longitudinal strain is nothing but del L by L. And these equations I am going to be simplifying. This is going to be longitudinal, I am going to be epsilon L is going to be your longitudinal strain plus 2 into lateral strain, that's already I am going to say epsilon T. That's going to be T into epsilon T. Further simplification of this one, epsilon L plus 2 into minus mu into epsilon L, I can take it. Can you see? Because epsilon L I have taken, because this epsilon T I can make it like this, epsilon T by epsilon L. Then epsilon T is equal to minus mu into epsilon L. The same equation I have substituted. Right? So then further simplification of this equation. So simplification, that's going to be epsilon V is equal to, So in this case, epsilon L is the common, 1 minus 2 mu we are going to be taking. That is the longitudinal strain. Epsilon L is equal to del L by L, 1 minus 2 mu we are going to be taking. Can you see the change in dimensions of that component we can define in respect to only the one change in dimension, that is going to be longitudinal direction. So that's going to be del L by L, 1 minus 2 into mu. Mu is going to be the Poisson's ratio. That's why that Poisson's ratio will helpful to you while you can convert into unknown parameters into the known parameters, because this member is going to be subjected to axial load, right, in the longitudinal direction. That means whatever the changes occurred in that member because of the longitudinal, right, that's why the total equations we converted into the longitudinal strain, right, that is going to be volumetric strain in terms of the longitudinal strain. So in this video lectures we have seen what is the volumetric strain. The strain is nothing but change in volume by to the original volume. And similarly, the same concepts we applied here, the volumetric strain of a rectangle bar when it is going to be subjected to the axial load. Only in x direction load is going to be acting. And how the lateral directions, the dimensions are going to be changing, that we have discussed. So I hope you are able to understand whatever we discussed. Thank you.